I'm a developer advocate at QuestDB, and QuestDB is a time series database. I really like databases. I've been working with databases for a long time, and I feel very often time series databases are not well known. So today I wanted to speak about why we need time series databases, what they are, and what's behind a time series database, how they work behind the scenes. And I'm going to be speaking mostly about what you can do with QuestDB, but actually many of the things I'm going to be saying today will be, in some way or another, they will apply to some other time series databases. So it's not going to be only about QuestDB, it's going to be more about the general concept of a time series database. But why we need to talk about time series databases? Well, the first thing is that working with timestamps can be quite hard. This tweet, it's a joke. I think it's quite fun, but actually it is true that every developer at some point or another had experienced some issues when trying to work with timestamps or with time zones, because they are not really straightforward. This is a stupid example. You don't need to understand the code, but we have here a string pointing to one particular second in time in 1927. Then we have another string which is pointing to 1 second after in time. If you do this in Java, and if you try to subtract one string from one date from the other, you should be expecting the difference between the two dates is 1 second, but in reality, the difference between this date and this other is 353 seconds. And why is that? Well, it's because, in the last day of the year in 1927, in China, they were doing a time zone adjustment, and they added 5 minutes and 52 seconds to the official to the official time on the time zone. That happens often. In some countries do adjustments. So if you try to work with time zones, you can find, some of these hidden surprises, which are not really super interesting. But it's not only about time zones. This, for example, is a timestamp. It's an epoch. But what is this date? Can you tell me? Or maybe not. But what if I tell you that this date is exactly the same as this other? When is this? Is this the 1st of April of 2019? Is the 19th of January of the year 4? I don't know. That's the thing. It's kind of tricky. So working with time and time zones sometimes is not that straightforward. And of course, these are kind of jokes, just to set the tone. But the thing is, working with timestamp data can be tricky, especially if you are doing this at a scale. So I'm going to be speaking today about time series databases, but I want to make one thing clear. I really, 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 really like conventional relational databases. So even if today I'm going to be speaking about time series databases, I don't mean here that you should use a time series database for everything. You should use time series databases only where they make sense. If you have a problem that can be solved with a conventional relational database, like for example Postgres, which is my personal favorite, then by all means use a relational database. The thing is, conventional relational databases are not designed for some use cases which are very common in the industry. For example, sometimes you need to ingest large amount of data, maybe several millions per day or even more than several millions of inserts per day. Relational databases are not really great when you are working with over a few hundred millions of data. In general, they don't perform very well with that. Very often, you want to do aggregations by arbitrary time units. For example, tell me what happened in the last 15 seconds, or in the last 100 microseconds, or in the past quarter, or those kind of arbitrary aggregations. You try to do that with a relational database. You can do them, but you need to start working with specific functions, extract parts from the date, group by, a lot of hassle for things that should be simple. Or if you try to find gaps, missing data, intervals of time where you didn't have any activity on the database, this sounds conceptually very easy, when you try to write a SQL, it's not really straightforward. Or if you have two different tables in which you have different events with very close timestamps, but not exactly the same, and you want to join by approximate timestamp, again, not easy to do. Or just if you want to aggregate over billions of records. And you might tell me, yeah, maybe aggregating over billions of records is not my use case, but who needs to aggregate over billions of records? Well, it turns out that getting a billion of data points is actually very simple. Imagine you have a factory and you have 500 machines, or you have only 50 trains with 10 cars on each train, or you have 500 users, and you are sending for each of these series, for one of these different 500 devices, you are sending a data point every second. This is the numbers of seconds that you have in one single day. This is the number of seconds that you have in 1 week. You see where I'm going here, yeah? This is the number of seconds that you have in a typical month. There is nothing like a typical month. Some months have 28 days, 29, 30, 31. So this is the number of seconds in the typical average month of 30.2 days, okay? So that means if you're ingesting 500 points every second in just below 1 month, you're going to have a billion data points already. And that's only for 1 month. And that's only for 500 devices, which is nothing. So in many use cases, you really, really, really need to deal with data that is going to be growing very fast. And you need to decide what to do with that. And you need to have some tool to work with this kind of, of data. And not all the data tokens are the same. And that's why we have time series databases. And time series databases, I don't care if it's QuestDB or if it's like any other database, like, I don't know, there are a lot of time series databases like InfluxDB or Timescale, Victoria Metrics, Dolphin, Amazon TimeStream, whatnot. So all of them have something which are in common. Of course, my favorite database is QuestDB, but all of them have something in common, which all of them are optimized for ingesting data, which is mostly append only, and it's coming fast. It can be coming slow, but they are optimized for data which is going to be growing pretty fast. They all have some sort of lifecycle policies, because when your data is growing so quickly, at some point you need to decide what to do with the old data. In a conventional use case, in a transactional operation, you wouldn't say, I'm going to remove a row in my table only because it's very old. But when we are speaking about time series and about analytical data, it's very often the case you won't remove or move to cheaper storage the older data. So all the databases and time series, they will give you some capacities for data lifecycle policies. All the databases and time series, they give you the tools to divide the time series in arbitrary chunks of time and doing aggregations, resampling the data, downsampling the data, those kind of things. I will show you later a lot of demos, so you see better what I'm talking about. And also a very common use case is that in many use cases, many occasions, these time series databases are going to be powering real-time dashboards. So these are some of the things that you're going to see in every time series database. But I want to talk today about the building blocks behind QuestDB, which is an open source database where I work and where I contribute. We are fairly popular. For comparison, in GitHub, we have over 30,000 favorites. For Postgres, which is way more popular than we are, they have 12,000 stars in GitHub. MongoDB, they have 23 or 24,000 stars. So, for a database, we are reasonably popular. We have some community around the project, and we've been around for a number of years already. So we are fully open source, Apache 2.0. So you can use QuestDB without any restrictions for any environment, totally for free. If you want, I will tell you at the end, we also have an enterprise offering and a managed version, a cloud offering. But if you want to use open source, QuestDB is Apache 2.0, you can use it for absolutely everything. And some things we like about QuestDB is like we are very performant. We believe we are the fastest open source time series database. Of course, Every other vendor is going to tell you the same, and they are all right, but we are the fastest. So we are pretty fast, even with smaller hardware, because it's kind of easy to be hard when you have a huge machine, but in smaller machines, we also perform reasonably well. We try to offer a good developer experience. I will show you later a few examples, so you can decide for yourself. As I told you, we are Apache 2.0, so fully open source. And the first building block of a time series database is being able to ingest data pretty fast. In our benchmarks with QuestDB, we have found that we can ingest up to over 4 million records per second on a single instance with 16 CPUs, which is kind of fast. It's faster than some other databases there. And these rows, by the way, in this benchmark, they are 10 numbers and 10 strings. So with 20 columns, we are able to ingest over 4 million rows. So what I'm going to do, I'm going to show you in my machine, the same machine from which I'm running this streaming, I'm going to show you a demo of ingesting data. So I have here local QuestDB up and running, and I have here 3 different shells, and I'm going to start a very small, a very simple Go script that is going to be sending, each of these windows is going to be sending 10 million records to QuestDB, to my local database running on the machine where I'm running this same stream. So right now, I just started, so I'm sending chunks of 10,000 records every time. If I come here to my interface, I can see, oh, sorry, that's not the one. This is actually the one. I can see I already ingested 28 million rows. I can see now it already finished ingesting the 30 millions. And I can see here, I'm sampling by second. So basically here, I'm going to make this bigger. So basically here, what I'm doing is like, I'm just selecting the count sampled by 1 second. So as you can see, in this machine, as I was speaking, I was ingesting data. In some seconds, I had 2.2, 2.3 million records, 1.8. So as you can see, it was pretty fast. Even if the machine is busy, it's a development machine, it's not optimized. But I have a fast drive, it's a Mac, so it was working reasonably well. So if I can get this on a machine without a lot of optimizations while running many other things, you can imagine we can perform pretty well on a server environment. So streaming is fast, and I'm going to tell you some of the things why this streaming is fast. When it comes to storing data, since we are designed only for time series data, we store the data always by incremental timestamp. And we store the data partition. When you create a table, you can choose if you are going to be partitioning by hour, by day, by month, by week, by year. So basically, we store the data partition. We store the data in a columnar format. The colleague from DuckDB who was speaking before, he was also explaining about the benefits of columnar format. So we also store data in columnar format. Since we store the data in columns and it's partitioned by time and data is incremental, it is very fast for us to locate a particular point in time and then analyze data sequentially, which is the use case for a time series database. That means that, as it was the case on the talk by DuckDB before, very often we don't need indexes. We have only one use case for indexes, but most users can work without indexes, and it's faster than actually using indexes. Your data is immediately available after writing, even if it's coming very fast. The ingestion layer is totally separated from the querying layer, so we have always a predictable ingestion rate. Even when you are running queries on top, you can still ingest data and it's going to be predictable, which is quite important for many use cases. We have the deduplication directly on the ingestion layer. So if you have data which is coming duplicates because of different reasons, we're going to remove the duplicates directly on ingestion. It's configurable. You can choose to keep the duplicates, but if you choose not to keep them for a specific table, we are going to just ignore the duplicates. We have some data types specifically built to take fewer space on disk, so we can be faster when writing and when reading. And even if we are optimized for appending data, we also support updates and upserts. So that's kind of like, behind the scenes, like super high level overview of the ingestion and storage layer on QuestDB. I told you earlier about lifecycle policies, what to do when data is getting old. So in QuestDB, you can do a few things. One thing will be just dropping the older partitions. You could say, hey, I want to remove this couple of days, or I want to remove everything which is older than a particular date. Or if you don't want to remove the partitions, something you can do is detaching the partitions. Detaching means they are not going to be visible anymore for the database, but they are still in disk. So something you can do, you can detach the partition, you can move it elsewhere to object storage maybe, or maybe you want to move it to a cheaper storage. Maybe your main drive is a very fast SSD and you have a cheaper magnetic drive, or maybe you are in cloud and you have different tiers of storage. So you can detach a partition and then you can reattach the partition, but linking to a different disk that might be cheaper, which means it will be slower, but you can save some money with that. You can just you can play how to work with partitions to delete them completely, or just move into cheaper storage, or you can even create a table on a different volume. So you might have different volumes with different capacities. Some might be faster and more expensive. Some might be cheaper but slower, and you can choose to keep some tables directly on different storage. So that's the lifecycle policies we offer you in QuestDB and how we help dealing with that kind of data. Actually, in the commercial offering in QuestDB Cloud and QuestDB Enterprise, we are also developing now cold storage, in which we can directly move data to S3 back and forth, but that's for a different talk. When it comes to connecting to QuestDB, you have different options. You can use just the web interface, which looks like this. It gives you some basic capacities for querying data. Let me just for a second. So you can just query data, and we have very basic charts capacity for showing some simple diagrams. Of course, if you want to use more advanced dashboards, you wouldn't do that directly on QuestDB. You can integrate with different dashboard solutions. This, for example, is a dashboard built on Grafana, and is querying real-time financial data from QuestDB. And if I look behind any of these panels here, what I'm doing is just running SQL against QuestDB. But for a proper dashboard, you will be using another tool like Grafana or whatever. But in the web interface in QuestDB, we have very simple chart capacities. So you want to do something quick, interactively, you can use QuestDB for that directly. We also have the PostgreSQL protocol. So you have a low-level library that speaks Postgres. You can use it for querying the data. You can also, if you want, ingest data using the Postgres protocol, but it's not really high performant. You can ingest maybe a few thousand rows per second maximum, but if you want to go over that, you have to use a different protocol that we offer. It's called ILP. It's socket-based, and it gives you very, very high throughput. And we have clients in 7 different programming languages. So it's very easy to get started because you have the integration directly with different languages. Of course, we have a monitoring endpoint if you want to monitor the health of QuestDB. And we integrate with different tools. We have native integration with Apache Kafka or with Apache Flink, with Python Pandas, with Grafana, as you just saw on the dashboard, with Telegraph, with RedPanda, and with many other tools just using the Postgres protocol. For some of those integrations are native, some of them use the Postgres driver. So that's kind of the high-level overview of QuestDB. One of my favorite parts is the query engine, which type of queries you can do in QuestDB. So the query engine has been super optimized for dealing with fast-moving data. We use mostly Java and C++. We don't have any dependencies. We do native memory management. We try to take advantage of the latest advantages of latest trends on CPU, on storage, data structures, file systems to have all the performance that it's possible. We implement our just-in-time compiler. We try to parallelize absolutely everything. And very often we can spend days or weeks just to optimize some functions in which we can save nanoseconds for some operations. And for us, that's quite important. We really want to be as performant as possible. But more than about the internals, I want to show you what you can do with a time series database. So we offer SQL just with time series extensions. And the first thing you can do when you're working with QuestDB is just this. I want to go to the demo site. This site, by the way, it's publicly available. You can come to this site. We have data sets available on this demo QuestDB.io. And something you might want to do is just saying, okay, I want to check just which data I have on this table. This table is a live table. We are reading data from Coinbase. This data is updating every second or so. So here I'm just checking the latest 500 rows. You can see I have here many different symbols, like, Bitcoin, Ethereum, whatever. But what if I want to find what was the latest row for each of the symbols that we are trading? I can just run this query. I want to select everything, but I want to get only the latest entry for each different symbol. And here what I have is the latest row I've seen for each different symbol I have here on this database. So it's very easy to get what happened last for each of the series I'm monitoring. Of course, I can combine this with different columns. I can say something like, for each symbol in this pair, I want to have the latest by symbol and site. So for each combination of different symbol and different site, I'm going to have the latest row, which is very convenient when you are trying to find or publishing a dashboard like the one I showed you before. This is what we are doing here. We are just getting the latest row for each of the symbols we are tracking, we are monitoring. That's kind of the very, very, very common use case for time series. Another thing you can do in time series is downsampling data or aggregating data in time intervals. And for that, I'm going to also show you here. In this query, what I'm doing is I'm just getting a select, and I'm doing just a sum, as you will do in any other, could be also an average, whatever, as you will do in any other database. But I'm not doing a group by, I'm doing a sample by. So basically what I'm doing here is I want to aggregate in 15 minutes intervals, and I'm going to run these aggregations in these 15 minutes intervals. And see in 15 minutes, but it could be any unit. It could be in 12 seconds intervals, or in 1 year interval, anything goes. You decide, the level of aggregation you want to have, arbitrary aggregations. So it's like a group by, but I'm grouping by time intervals, not really by any, well, in this case, I'm grouping by time intervals and timestamp. I could be grouping by time intervals and timestamp and symbol, for example. So you can combine grouping by interval and also by different columns, but you get the idea, yeah? So once you have this, when you can group by intervals, something which is pretty cool is that you can ask your database to find which data is not stored on your database. For example, imagine you are sending data every second and you want to check if you have any device that was not sending data in more than 1.5 seconds intervals. So if you want to do this, I can just take the query I was just using a second ago, and I can do this. I can say, I want to aggregate in 1 second intervals. If I find any gaps, I want to fill with a null value. So I can very easily find in which intervals I'm not sending any data. Of course, I can fill with different strategies. I can fill with a linear interpolation. I can fill with a constant. I can fill with different values. But the idea is you can find very easily any intervals. In this case, I'm doing 1 second intervals. I could go to find me, 500 milliseconds. You can play and get anything you want here, okay? I want to move on because I have only a couple of minutes left here. So of course, we have also optimizations to work with time ranges. For example, if I want to work with only 1 month of data, I can just say where the date time is in this format or in this other, and it's going to analyze only 1 month, only 1 minute, only 1 second. You can put there which is your strategy, but the one I really like, we have this extension in which you can do, I want to find all the trips that happen from this point in time and 4 seconds afterwards, so around midnight, 2 seconds before and 4 seconds after, so 2 seconds and before and 2 seconds after midnight, for every day from this particular date and 7 days afterwards. So this is finding me. It starts in this particular second and is going for 7 days, finding the 2 seconds before and after midnight. And I can do this also in negative. So I want to position myself 7 days before this particular date, and I'm going to analyze what happened 2 seconds before and after midnight. As you can imagine, for many use cases, having these semantics is super interesting. And if you try to do this on a conventional database, or even in other time series databases, it's going to be very tricky with the SQL you have to use, okay? So one more example, and I'm finishing with this. What if I have two different tables in which I have timestamps, but they are not aligned? So in this, also in this demo site, I have a table representing taxi rides in New York, and I have another table representing weather in Manhattan. The taxis in New York, I have one entry every, several entries actually per second, because I have several trips finishing in New York every second. For the weather stations, I have only one entry or two per hour. But what I can do what we call an as of join, which basically takes the timestamp from the first table, the timestamp from the second table, and is going to find the closest matching record in the second table, which is matching the first one. So as you can see, all the records in the first table are moving pretty fast, but they are all matching to the same record in the second table. If I change here to another point in time, for example, this point in time, you will see now we are matching to a different record on this table, but we are finding automatically the closest matching timestamp without being an exact match, which is actually quite interesting. So these are the kind of things you can do on on QuestDB, on a time series database. Of course, we are working now to have more optimization for performance. So at some point in the future, we'll be adding things to be even more performant to let you do more things. But I'm getting to the end of the talk. So what's left for me to say is that if you want to use QuestDB open source as of today, you can go to GitHub, Apache 2.0, use it for anything. If you prefer to use cloud, we have a managed version. In this case, it's pay as you go. You pay for the size of the machines that you are starting, no more and no less. And if you are an enterprise and you want to have self-hosted QuestDB, but with enterprise features, we also have licenses QuestDB.